Hi all, welcome you back to the lecture video session on generalized constants analysis of the short transmission lines. In the previous video, we were discussing about the short transmission line equivalent circuit and how to apply the generalized constants A, B, C, D parameters to the short transmission line network and analyze what are the transmission line parameters. So we were comparing the standard equation of Vs and Is along with the equation that is written for the equivalent circuit of Is and Vs. Now we found that A is equal to 1 and B is equal to Z and C is equal to 0 and D is equal to 1 because there is only one parameter that is associated with this, that is D into IR. It should be equated to the Is equation where Is is equal to IR. So A equals 1, B equals Z, and then the C vector is equal to 0 and then the D vector is equal to 1. We can see that A is equal to D here because A is also 1 and D is also 1. Hence the network is said to be symmetrical. And that now AD minus BC is equal to A into D. A is 1 and D is also 1. 1 minus B is Z and C is 0. So it is found to be 1. So AD minus BC will also hold good to 1. So the network is found to be symmetrical, as well as the network is also seen to be reciprocal also because AD minus BC is also equal to 1. Now, after learning that the short transmission line is symmetrical and reciprocal, we can move on to the medium transmission line, where in the medium transmission line, we can consider three different methods. One is the end condenser method, second one is the nominal T method, and then the third one is the nominal pi method. For the convenience, we are going to consider two different type of performance analysis using nominal T method as well as nominal pi method. Let us take the first one, where the capacitance is considered to be existing at the center of the transmission line, or it is lumped or concentrated at the center of the transmission line, where the impedance is considered to be halved into two sides of the capacitance. So a figure shows the equivalent diagram of the medium transmission line with the nominal T network representation. Now the load is considered to have the receiving end voltage of VR. R divided by 2 plus XL divided by 2 on either side constitutes Z divided by 2 as impedance of the circuit, and the voltage across the capacitance at the center is considered to be V1, and C is considered to be the capacitance, XC is considered to be the capacitive reactance, Vs is considered to be the sending end voltage, and Is is considered to be the sending end current, and IR is considered to be the receiving end current, and Is is nothing but the vectorial sum of IC and IR. Now, after considering this, again as a procedure, we are going to consider the equations that is written based on the equivalent diagram with the standard equations of ABCD. Let us write the equations for this equivalent line. So Vs, that is the sending end voltage, is nothing but equal to V1 plus Is into Z divided by 2. V1 is the voltage across the capacitance. So V1 plus Is into Z divided by 2. Now V1 is nothing but, now we can write that V1 is equal to VR plus IR into Z divided by 2. V1 is nothing but IR into Z divided by 2 plus VR. Now keep this equation as a sending end voltage as a 14. Equation 15 shows the voltage across the capacitance. Now also we can say that Is is equal to vectorial sum of IC plus IR. IC is nothing but equal to V1 into admittance of the circuit, that is Y. So Y is a shunt admittance. Is is equal to V1 into Y, that is IC plus IR. So here we can take VR. V1 is nothing but equal to VR plus IR into Z divided by 2 into admittance plus IR. Now simplify the equation. VR into Y plus IR into IR is the common between these two. So IR into Y into Z divided by 2 plus 1. Now writing the equation Is is equal to Y into VR plus 1 plus Y into Z divided by 2 whole multiplied by IR. Substituting this value of V1 in the equation 14, where the equation 14 is Vs is equal to V1 plus Is into Z divided by 2. Substitute this Is factor here from the equation. We will get Vs is equal to VR plus IR into Z divided by 2. So Vs is equal to Vr plus Ir into Z divided by 2 plus Z by 2 is common here. Z by 2 into whole multiplied by Y into Vr plus 1 plus Yz divided by 2 into Ir. Follow the steps and then simplify this. We will get to see that Vs is equal to 1 plus Yz divided by 2 into Vr plus Z square into Z vector square multiplied by Y, that is the admittance, shunt admittance, divided by 4 multiplied by IR. So IS is equal to Y into VR plus 1 plus YZ divided by 2 into IR. So comparing the above equations with the standard equations, we can get Vs is equal to A into VR plus B into IR and Is is equal to C into VR plus D into IR. These are the standard set of equations. So A is nothing but equal to D, that is equal to 1 plus Y into Z divided by 2, and B is nothing but equal to Z plus Y into Z square divided by 4, and C is nothing but equal to Y shunt admittance. So A, B, C is known as A, B, C and D is known. So A is equal to D and B is equal to Z plus Y into Z square divided by 4, and C is nothing but equal to Y. Now after this, as we can see here that A is equal to D, so the circuit is said to be symmetrical, and AD, let's find out the condition for the reciprocity of the network. AD minus BC is equal to A is 1 plus Y into Z divided by 2 into D, again Y 1 plus YZ divided by 2, minus B is nothing but equal to Z plus Y into Z square divided by 4, and C is nothing but equal to Y. So multiply this and then simplify the equation. We will get to see that AD minus BC is also equal to 1. So the network is seen to be reciprocal also. So using the nominal T method and by applying the generalized constants, we can understand that medium transmission line with the help of the nominal T method is also found to be both symmetrical as well as reciprocal. So now let's move on to the nominal pi method, where the capacitance is assumed to exist on both the ends, that is on the half of the capacitance is assumed to exist on both sending end as well as the receiving end. So here we have written the equivalent circuit of the nominal pi method of medium transmission line, where C1 and C2 constitutes the Y by 2, that is the capacitance on both the ends of the transmission line, that is one is at the receiving end and the other one is at the sending end. So the entire impedance is supposed to exist between these two capacitances. So R and XL constitutes the impedance of the line. IS is the current that is flowing from the sending end, and IL is the current that is flowing through the impedance of the line. IC1 is the current flowing through the capacitance 1, which is at the receiving end. IC2 is the current that is flowing from the flowing through the capacitance which is at the sending end. And IC1 and vectorial sum of IC1 and IR constitutes the load current IL, and the vectorial sum of IL and IC2 constitutes the sending end current IS. Now let's see that how to find out whether the network is symmetrical and reciprocal or not. In the nominal pi method, Z is nothing but equal to R plus JXL, Y is nothing but equal to J into omega C, that is a shunt admittance is nothing but J into omega C. IS is equal to IL plus IC2, that is IC2 is equal to Vs into Y divided by 2. From this we can write that IC2 is nothing but Vs multiplied by Y by 2. Similarly, IC1 is nothing but VR multiplied by Y by 2. Now IL is nothing but equal to IR plus IC1, as I already told. IR plus IC1 constitutes the IL, and that is IC2, and here this is nothing but equal to IL is equal to IR plus IC1. IR plus IC1 is nothing but equal to VR into Y divided by 2. Similarly, Vs is nothing but equal to VR plus IL into Z. VR plus IR plus IL into Z. IL into Z is IL is nothing but IR plus VR into Y divided by 2 into Z. Similarly, write the equation for Vs is equal to 1 plus, take the common out. So 1 plus YZ divided by 2 into VR plus IR into Z. So now IS is nothing but equal to IL plus IC2, which is nothing but equal to IL is nothing but IR plus VR into Y divided by 2. IC2 is nothing but Vs into Y divided by 2. So simplify the equation, we get VR into y divided by 2 plus y divided by 2 plus y squared into z divided by 4 plus IR into 1 plus yz divided by 2. So IS is nothing but equal to y minus z into y square divided by 4 plus into multiplied by VR plus 1 plus zy divided by 2 multiplied by IR. Again simplify the equation by taking the y out. So IS is equal to y is the common factor, y into 1 plus yz divided by 4 into VR plus 1 plus yz divided by 2 into IR. Compare the equations of Vs and Is with the standard equations given by Vs is equal to A into Vr plus B into IR and Is is equal to C into Vr plus D into IR. Now we have A is equal to 1 plus yz divided by 2 is that is equal to D and B is equal to Z. Compare these equations. Vs is equal to A into Vr plus B into IR. What is the equation for Vs here? Vs is equal to 1 plus yz divided by 2 into Vr plus z into IR. Now if we compare these two equations, A into Vr, so A is nothing but equal to 1 plus yz divided by 2 which is also equivalent to D and in this equation. So B is nothing but equal to Z and C can be compared with this equation. C, from this you can say that C is equal to 1 plus y into z divided by 4 multiplied by y, that is y into 1 plus yz divided by 4 is C. So comparing these equations we got to see that A is equal to D and B and C. Now since A is equal to D, the network is found to be symmetrical on either side and AD minus BC can also be seen here. AD minus BC is equal to A is 1 plus yz divided by 2, again D is also 1 plus yz divided by 2 minus B is nothing but Z multiplied by y into 1 plus yz divided by 4. So by simplifying the equation we can see that AD minus BC is also equal to 1. So the network is said to be reciprocal also. So both medium transmission line as well as short transmission line is found to be symmetrical and reciprocal about its equivalent diagram. So using this assumptions by understanding the generalized constants A, B, C, D parameters by applying to short transmission line and then the medium transmission line, we can solve many of the tutorial problems to find out what is the transmission line efficiency as well as the regulation. I have considered one of the problem here where A is 110 kilovolts 50 hertz 3-phase transmission line delivers a load of 40 megawatt at 0.85 lagging power factor at receiving end. The generalized constants of the transmission line A is equal to D is equal to 0.95 at an angle 1.4 degrees, B is equal to 96 at an angle 78 degree ohms, C is equal to 0.0015 at an angle 90 degree mho. So find the regulation of the line and then the charging current using the nominal T method. The moment we get to see that nominal T method, it is a medium transmission line. Also the another reference is that it is above 100 kilovolts, that is 110 kilovolts, and here we can write the equivalent diagram of nominal T method for a transmission line, and R divided by 2, XL divided by 2, C, and then the load across the voltage across the receiving end, that is VR. Now we know that VR is given from the equation from the problem, that is 110 kilovolts, and delivery end power is also given 40 megawatt. Now since it is given 110 kilovolts, we need to find out the regulation of the line and charging current using the nominal T method. Let's understand the receiving end phase voltage is 110 kV that divided by root 3 we are going to have the phase voltage of 63.50 kilovolts, and receiving end current can also be found out using the power, that is IR is equal to power at the receiving end PR divided by root 3 into VR into cos phi R, because we know that the power at the receiving end is equal to root 3 VR IR cos phi R. Now using this we can say that power at the receiving end 40 into 10 to the power 6 divided by root 3 into 10 into 10 to the power 3 into 0.85, that is 247 amperes. Now IR is equal to 247 at an angle minus cos inverse 0.85, that is 247 at an angle minus 31.78 degree amperes. Vs is equal to So now what is the standard expression for Vs in terms of A and B? Vs is equal to A into Vr plus B into IR. So we know the values of A, B, C, D in the problem itself it is stated. So using this we can find out the sending end voltage. A into Vr plus B into IR, apply all the values which is given in the problem, and we will be able to find out that Vs is nothing but equal to 78,942.301 at an angle 13.62 degrees. In magnitude, Vs is equal to 78.942 kilowatt. Now, kilovolts. Now, we can find out that sending end current is nothing but equal to Is is equal to C into Vr plus D into IR. This is the standard expression. So we know that C value, we know the D value, we know Vr. We can substitute all these values and then we can find out that the current Is is nothing but equal to 203.77 at an angle minus 6.5959 degree amperes. So now we have for nominal T method, Is is equal to Ic plus IR. This is what we have found out. Is is equal to Ic plus IR. Charging current is Ic, that is charging current Ic is flowing through the capacitance. Ic is equal to sum of Ic is equal to Is minus IR from this expression. So now Is minus IR is nothing but equal to 203.77 at an angle minus 6.5959 minus IR is the current that is flowing through the receiving end current, that is 247 at an angle minus 31.78. Substitute this, we will get Ic is nothing but equal to 106.93 at an angle 94.04 degree amperes. By magnitude, Ic is equal to 106.93 amperes. Now after knowing this, percentage voltage regulation can be calculated as VRO minus VR divided by VR. What is the expression for the voltage regulation? It is nothing but equal to the no load to full load. So we can say that VRO is nothing but equal to Vs divided by A minus VR divided by VR. So Vs nothing but Vs is nothing but 78.942 kilovolts divided by 0.95 minus 63.50 kilovolts divided by 63.50. So now we can calculate what is the percentage voltage regulation. 30.86% is the percentage voltage regulation. Now we considered in the earlier problem, we considered the nominal T method. Now we can go with another type of problem where we need to find out ABCD constants. Earlier ABCD constants were given and we were asked to calculate what is the percentage voltage regulation. In this tutorial problem, ABCD constant need to be found out and by giving the other parameters. Now the problem is very simple. Problem is a balanced three-phase load of 50 megawatt is supplied at 132 kilovolts, 50 hertz and 0.8 power factor lagging by means of the transmission line. Now with this we can understand that so we can understand that the network is given, so that is nominal T method, and then the total phase to neutral admittance is given 310 into 10 to the power minus 6, and with this 310 into 10 to the power minus 6 we can have series impedance of the single conductor 20 plus J50 ohms is also given. Since the capacitance is at the mid, we need to know that 20 plus J50 appears on both the sides. Now let us see that what needs to be done in this problem is that we need to find out in the problem that is asked ABCD constants of the line, sending end voltage and then the regulation of the line. Now to find out that ABCD parameters, we need to have the set of standard equations as well as equation to be written for the equivalent diagram of the T network, that is nominal T network, which is written according to the parameters that are given. So now as we have understood that medium transmission line with the nominal T network, we found out that the standard equations for this A is equal to D is equal to 1 plus Z into Y divided by 2. Now 1 plus Z into Y divided by 2, Z is already given and then the shunt admittance